Welcome to the session on solution of differential equations using Runge-Kutta method. The use of the previous methods to solve the differential equation numerically is restricted due to either slow convergence or due to labor involved, especially in Taylor's series method. In Runge-Kutta methods, the derivatives of higher order are not required, and we require only the given function values at different points. Since the derivation of the fourth order Runge-Kutta method is tedious, we will here derive the Runge-Kutta method of second order. To solve the differential equation of the form dy by dx is equal to f of x y, given that y of x naught is equal to y naught, we shall derive the second order Runge-Kutta method to solve this first order differential equation having this initial condition. By Taylor's method, we have not Taylor's method, by Taylor series, we have y of x plus h is equal to y of x plus h into y dash of x plus h square by 2 factorial into y double dash of x plus O of h cube, where O h cube denote the terms having higher powers of h. Now, we differentiating this differential equation with respect to x, we get this equation can be written as y dash is equal to f of x y. Differentiating with respect to x, we get y double dash is equal to dou f by dou x. The right hand side is a function of x and y, therefore, the derivative is dou f by dou x plus dou f by dou y into dy by dx. That is equal to f x, we denote this notation f x for dou f by dou x plus y dash, we use y dash for dy by dx into f y. F y is dou f by dou y. That is equal to f x plus f into f y, because y dash is f of x y. For convenience, we write f for f of x y. Y dash is f into f y. That is y double dash is equal to f x plus f into f y. Using the value of y dash and this y double dash, we can write this expression as y of x plus h is equal to y of x plus h into y dash of x. We use y dash y dash x is equal to f of x y, and y double dash x is equal to f x plus f into f y here. Therefore, we can write y of x plus h, we transpose this y of x into the left side, y of x plus h minus y of x is equal to h into y dash of x is f of x y. For convenience, we write f for f of x y plus here 2 factorial in the denominator, 2 factorial is 2. Therefore, we can write 1 by 2 into h square y double dash is fx plus f into fy. Plus OH cube. Now, we use the notations delta y, which is equal to here y of x plus h minus y of x, which is denoted as delta y, which is equal to h into f plus 1 by 2 h square into here fx plus f into fy plus OH cube. Now, we use these notations delta 1y, which is equal to k1, that is f of xy, f of xy into delta x. Delta x means h into f of xy, that is k1 is equal to h into f of xy, delta 2y as k2, which is equal to f of x plus mh comma y plus m k1, and delta y as a into k1 plus b into k2. These constants a and b are constants to be determined to get the better accuracy of delta y. Now, we expand k2 and delta y in powers of h. This is our k2. K2 is f of x plus mh comma y plus m k1. First, we expand this k2 in powers of h by using the Taylor series for two variables. We have k2 is equal to f of x plus mh comma y plus m k1, which is equal to h into f of x comma y plus m into h into dou by dou x plus m into k1 into dou by dou y, this into f of xy plus m into h into dou by dou x plus m into k1 into dou by dou y, the whole square divided by 2 factorial into f of xy plus etc. This is by the Taylor series expansion of two variables, which is equal to h into, this is equal to h into f of xy is f plus m into h into dou by dou x of f means dou f by dou x. We use this notation fx for dou f by dou x plus m k1 into dou f by dou y. Dou f by dou y is fy plus here mh dou by dou x plus m k1 dou by dou y whole square divided by 2 factorial of f plus etc. Here k1 is equal to h into f. K1 is h into f. We use k1 equal to h into f here. We can write this is equal to h into f plus mh fx plus m into k1 is h into f, m into h into f into fy plus this term mh dou by dou x plus m k1 dou by dou y the whole square divided by 2 factorial of f plus etc. which is equal to, we can write this as h into f, that is hf, plus here h into mh is mh square into fx, plus here also h into mh, that is h square or m into h square f fy. Therefore, mh square can be taken as common factor, this into here fx plus in this case f into fy plus higher powers of h. We are neglecting the higher powers of h, or we write O of h cube, terms having the highest powers of h. This is K2. K2 is equal to hf plus mh square into fx plus f into fy plus OH cube. Now, we substituting this these values of K1 and K2. We get delta y as in this expression. For delta y we substitute K1 and K2, we obtain delta y is equal to here a into K1, where K1 is h into f. Therefore, we can write a into h into f plus b K2, where K2 is hf plus mh square into fx plus fy plus of h cube, this plus b into hf plus mh square into fx plus fy plus OH cube, terms having highest powers of h, which is denoted by OH cube. This is equal to here, from here a into h into f plus in the second term b into h into f. Therefore, we can write a plus b into hf plus here b m h square fx plus ffy, b m h square into fx plus fy plus OH cube. This is the expression for delta y obtained by substituting K1 and K2 in this expression. Now, we have delta y is equal to this expression also. Delta y is h into f plus 1 by 2 h square into fx plus fy plus of h cube, comparing these two expressions. We can write here h into f in this case h into f into a plus b. Therefore, this a plus b should be equal to 1. We can write a plus b is equal to 1, and here h square f x plus f into f y, h square f x plus f into f y, b into m is equal to 1 by 2. Bm is equal to 1 by 2. Now, from this a plus b equal to 1, we can write a is equal to 1 minus b. From this we can write a is equal to 1 minus b, and from this equation we can write m is equal to 1 by 2b, 1 divided by 2b. Therefore, we can write delta y as a is 1 minus b and b is 1 by 2b. Substituting values of a and b in this expression, we can write delta y as 1 minus b into k1 plus b into k2, that is b into k2, where k1 is equal to, or k1 is h into f, f means f of x y, k2 is equal to this f of x plus mh plus comma y plus mk1, that is k2 is equal to, or k2 is f of here h is missing, h into f of x plus mh comma y plus mk1, which is taken as k2. Therefore, k2 is h into f of x plus mh, x plus m is 1 by 2 into b, that is x plus 1 by 2 into b into h. Therefore, h by 2 into b, sorry, h by 2b, comma y plus mk1, that is hf divided by 2b. Because k1 is hf, m is 1 by 2b. Therefore, k2 equal to h into f of x plus h by 2b comma y plus hf by 2b. Now, delta y is equal to y of x plus h minus y of x. Therefore, we can write from here delta y is y of x plus h minus y of x, which is equal to 1 minus b into k1 plus b into k2. Therefore, we can write y of x plus h as y of x plus h is equal to y of x plus 1 minus b into k1, that is 1 minus b into k1 is h into f plus b into k2, b into k2 is h into f of x plus h by 2b comma y plus hf by 2b. This is the expression for y of x plus h. Therefore, we can write the general expression as yn plus 1 is equal to yn plus 1 minus b into h into f of x and yn plus b into h into f of x n plus h by 2b comma y n plus h by 2b into f of x n y n. bh into f of x n plus h by 2b comma y n plus h by 2b into f of x and y plus O of h cube. This is the general expression for y n plus 1. From this general second order Runge-Kutta formula, if we set A is equal to 0, B is equal to 1 and M is equal to 1 by 2, we obtain the second order Runge-Kutta algorithm as K1 is equal to h into f of x comma y, K2 is equal to h into f of x plus 1 by 2h comma y plus 1 by 2 K1, and delta y is equal to K2, where h is delta x. This is the second order Runge-Kutta algorithm, which is obtained by setting A equal to 0, B equal to 1 and M is equal to 1 by 2 in this general expression for Runge-Kutta formula. Now, the derivation of third order and fourth order Runge-Kutta algorithms are very tedious. We just state the algorithms. The third order Runge-Kutta algorithm is, this is second order. Next is third order Runge-Kutta algorithm, which is K1 is equal to h into f of x comma y, K2 is equal to h into f of x plus 1 by 2h comma y plus 1 by 2 K1, K3 is equal to h into f of x plus h comma y plus 2 K2 minus K1. This is the expression for K3, and delta y is equal to 1 by 6 into K1 plus 4 K2 plus K3. This is the third order Runge-Kutta algorithm. The derivation of this algorithm is very tedious. Therefore, we are stating the algorithm only. The fourth order Runge-Kutta algorithm is, next is fourth order Runge-Kutta method algorithm. K1 is equal to h into f of x y, K2 is equal to h into f of x plus 1 by 2h comma y plus 1 by 2 K1, K3 equal to h into f of x plus 1 by 2h comma y plus 1 by 2 K2. K4 equal to h into f of x plus h comma y plus K3, and delta y is 1 by 6 into K1 plus 2 K2 plus 2 K3 plus K4. Y of x plus h is equal to, from this expression we can write y of x plus h as y of x plus delta y. This is the fourth order Runge-Kutta algorithm. This algorithm is mostly used in practical applications. Now, consider an example for the Runge-Kutta method. Solve using Runge-Kutta method to find the solution of the differential equation y dash is equal to x plus y. Y dash is equal to x plus y given that y of 0 is equal to 1. We have to solve this differential equation to find the value of y of 0.1. Here x naught is taken as 0, y naught is 1. We want to find y of 0.1, means we can take x1 as 0.1. Here h is not mentioned, therefore we select h as 0.1. Now, by Runge-Kutta algorithm, we have algorithm K1 is equal to h into f of x y, K2 equal to h into f of x plus 1 by 2 h, comma y plus 1 by 2 K1, K3, K4, delta y and y of x plus h. Here f of x y is the right hand side function x plus y. X naught is 0, y naught is 1, x1 equal to 0.1, h is equal to 0.1. Therefore, we can find K1 as h into f of x naught, y naught. That is 0.1 into f of x naught plus y naught, because f of x y is sum of the two coordinates x and y. Therefore, here f of x naught y naught means f of x naught plus y naught, that is f of 0 plus 1. Sorry, f of 0 comma 1, that is 0.1 into 0 plus 1, that is equal to 0.1. K2 equal to h into f of x plus 1 by 2 h comma y plus 1 by 2 K1, that is h into f of x naught plus h by 2 comma y naught plus K1 by 2. On substituting the values of h, x naught, y naught and K1, we get 0.11. K3 is equal to h into f of x naught plus h by 2 comma y naught plus K2 by 2. After substituting the values of x naught, y naught, h and K2, one simplification we get K3 as 0.1105. Similarly, K4 can be obtained as 0.12105. Substituting these values of K1, K2, K3 and K4, we get delta y as 1 by 6 into K1 plus 2 K2 plus 2 K3 plus K4. On simplification, we will get delta y as 0.11034 1667. and therefore, y of x plus h, that is y of x naught plus h, that is y of x1. Y of x1 is y of 0.1. Here x1 is 0.1, which is equal to y of x naught plus delta y. Delta y is this, that is y of x naught is 1 plus delta y is 0.1103416667, which is approximately equal to 1.11034, correct to 5 decimal places. This is the required value of y of 0.1 approximately. With this example, let me conclude this session. In this session, we discussed the Runge-Kutta method of solving the differential equation of the form dy by dx is equal to f of x y, given that y of x naught equal to some y naught. Hope that you have understood this session. Thank you for listening the class. Have a nice day.